this context. If you have a few minutes, maybe you can quickly check and answer in Discord directly. So thanks a lot, Matthias, for the talk. And let's now, maybe you can disable your screen and let's move on to Sabine Suesstrunk. You can already share. Sabine Suesstrunk leads the Image and Visual Representation Lab in the School of Computer and Communication Sciences at EPFL since 1999. And she's broadly interested in computational photography, computer vision, machine learning, computational imaging, and more. She is famously known for her slick superpixel algorithm. Probably you have already used it, and also her work on saliency and salient region detection. She has won the ISNT 2013 Electronic Imaging Scientist of the Year Award and another award for the dedication in preparing the next generation of imaging scientists. And she will tell us today about semantic editing with generative adversarial networks. I'm looking forward to your talk.
Thank you very much, Andreas, and thank you very much for the invitation. And hello to everybody online that I'm, of course, not seeing, but I hope you'll have a good time. So I'm going to present today our CVPR 2020 paper, Editing in Style, uncovering the latent semantics of GANs. So this is actually work with my brilliant former PhD student, Ada Collins. He now is at Google, and our two colleagues, Raja and Bob from Palo Alto. So this work was actually done while both Ida and I spent a few weeks in a park last summer. Wouldn't have been possible this summer. So as this is a CVPR paper, what I'm going to do is I'm going to show you the teaser video first, and then I'll walk you through the method. So I'm going to just start the video and not going to say too much about it. So now look at the eyes, how the eyes change considering the reference. Now look at the nose, how the nose changes. And now, of course, look at the mouth, how the mouth changes. Here you have cabin, bumper, and wheels to actually look at. And also notice, because this is localized editing, sometimes the changes are quite subtle. Okay, so let me now walk you through it now that you've seen what this whole thing is all about, and basically go into a little bit more detail. So oops, sorry, let me just, okay, let's first talk a little bit about GANs. So most of you are familiar with it, but just to some of you who might be new to this topic, GANs are basically generative adversarial networks, as the name says, and was first introduced in 2014 by Goodfellow and his colleagues. Now, GANs are basically a class, basically consists of two networks. One is a generator and one is a discriminator. And what the generator takes as input is a random variable, usually just some kind of random noise, and generates an image that it feeds the discriminator, which has learned from real data sample what the image should look like. And then the discriminator basically determines is the image a real or a fake. Now, this, of course, you know, you feed back the feedback, you kind of backpropagate, this goes through several kind of examples until basically the generator is good enough that it can create an image that can fool the discriminator. And in 2020, the quality of the image synthesis has improved tremendously. Here I'm showing you 2 images that were done by StyleGAN 2, which was first published at the end of last year. One is a GAN trained on the flicker faces, high quality flicker faces, FFHQ dataset, and the other one on the LSUN-Cats dataset. And you really have to look kind of closely. Maybe here in the ear you could actually see that it's not quite, you know, maybe not quite correct, but on first regard you can basically fool everybody. Now here, these GANs, by the way, or the last generation GANs, have actually been introduced by NVIDIA. There's a good reason for that, because training this model is still a challenge and, you know, take a lot of time. So, but the PG-GAN, and I'll go into detail a little bit later, the progressive growing GAN has a little bit helped in the training or in the time it takes to train these GANs. And then StyleGAN and StyleGAN 2 are basically improved version of this PG-GAN. Again, these are relatively recent developments. StyleGAN was, as I said, first published at the end of 2019 and basically published then at GCPR 2020. So I'm going to show you an example here. So we have 2 synthetic outputs of StyleGAN, FFHQ, and we'll take one as the reference, and then we transfer localized the style of the reference onto the target. And we basically find out by distangling the generator layers of the GAN, or distangling the semantic localized characteristics that we have in the generator layers of the GANs. And so we can actually then transfer the style localized. So one on the middle image, you're seeing that we actually changed the eyes, given the reference image. The one on the middle, we changed the nose, and the one on the right, we change the mouth. So our method is actually very simple and effective because we require really nothing more than an off-the-shelf pre-trained GAN. So we're actually taking the StyleGAN 2 that NVIDIA published, and we're basically just analyzing these pre-trained GANs. We do not retrain our GANs. And our method is also quite unique in the sense that we enact a localized change through a global operation. It's akin to style transfer, and this is why we're using the word style. You know, as a result, unlike the other GAN editing methods that have been published so far, we don't need any additional data sets or trained networks or any image morphing methods to actually do complex spatial editing. We really just rely upon and benefit solely from the rich semantic representation learned by the GAN itself. So, what do we do? First of all, our method is actually inspired by a previous work that Edo has done during his PhD and that he published in ECCB 2018. There, we actually applied non-negative matrix factorization to deep convolutional feature maps A, obtained from VGG and reset CNNs trained on ImageNet. One more time, we did not retrain anything. We basically took pre-trained ImageNets. So given a few images as input, here we would have 3. We take the feature maps A from a deep layer, usually the last layer, before the fully connected layers, and stack them in a matrix on which we perform non-negative matrix factorization, resulting in a U and V matrix with K dimensions. And of course, K, we can choose to rank K as we wish. The matrix U is then reshaped into a tensor, which produces K sets of heat maps. And we found that these heat maps show very good overlap with semantic objects and object parts. So here's an example. So this is pre-trained PG-19 on the ICOSEC images. Now for K equals 1, you can see that the heat maps very well localize the dancer, or on the right-hand side, very well localize the elephants. K equals 2, you can see that the heat maps now show either the body or the limbs. So the blue heat map shows the body and the limbs, and quite similarly, for the elephant, you see the body and the legs. K equals 3 can distinguish now into objects parts. So we have the body, the arm, the legs, and it actually follows all through. Similarly in the elephants. And for K equals 4, we even include actually the bar. So keep in mind, the PG-19 on ICOSEC has never seen these images before. So they were not trained. They were just basically, we just kind of fed these 5 images in there and could extract basically heat maps that correspond to object and object parts. Now here is just an example. This is basically the same similar thing, but just to show you that it also works with a different kind of network. This is pre-trained on ResNet 50 on the Oxford and Paris buildings images, and you can see that it actually can do relatively well. Also, it can find even here the Notre Dame, the pyramids. Then here you can see the entrance of the Notre Dame, and then at this point in time, you can actually see some additional kind of features, which, keep in mind, you actually have to choose the K yourself, because if you choose K too high, it can become somewhat meaningless. So we're basically doing exactly the same thing with a GAN generator network. Now let me say a few more words about PG-GAN. So I said before that the researchers really had troubles generating high quality large images, so in the 1024 by 1024, until the PG-GAN came along. So NVIDIA actually produced PG-GAN, and the key innovation PG-GAN is the progressive training. So you start actually training the generator and the discriminator with very low resolution images. So in this case, 4 by 4, and you add a higher resolution layer every time. So this technique first creates the foundation of the image by learning the base features, which appear even in a low resolution image, and learns more and more detail, over time as the resolution increases. So in training the low resolution images, not only easier and faster, it also helps in training the higher resolution levels, and as a result, total training is faster. Now, StyleGAN and StyleGAN 2 use the same kind of architecture for the discriminator, but they actually are adding some more complexity to the generator. So we basically work on these levels, but instead of using NMF, we use spherical k-means. So we factorize under the constraints that the rows of U are 1/2 and the rows of V are unit vectors. Now, which layers and which factorization rank K do we choose? Well, this is where the manual part comes in. So we do have to test multiple levels. So here, for example, I will give you an example here. These are the flickle faces outputs that we can get with StyleGAN. And then here, for example, on the layer 32 by 32, we do spherical k-means with K equal 2. And you can see very clearly, it can distinguish between face and background. Then K equals 3. Here now you already have face, background, and you can see that eyes and mouth have a different kind of, belong to a different kind of cluster than the face. K equal 10, now we're already getting very sophisticated. Now you can see the hair is one cluster. You can see the nose is one cluster, the eye, then the upper level lips and the lower level lips, and of course the chin. And then you go to 25, and now it becomes a little bit more difficult to interpret, but you can still see similar clusters. An example now, layer 128 by 128, k equals to 25, and now you can see, okay, yes, you can still see some, as you can see from maybe the eyes, is still the same cluster everywhere, but the rest becomes very difficult to interpret. And when you go up to 256 by 256, same thing happens. You can still see one cluster like the eyes who are more or less consistent, but the rest seems to be going anywhere. And here is 512 by 512, k equals 25, and the same thing happens here. So what we realized, the lower layers have much greater control over the shape and the higher layers of the texture, but that has actually been known before, and we heard him in the previous talk kind of alluded to this. So, you know, our new insight basically was that an intermediate layer, in this case actually 32 by 32, the faces are really spatially disentangled into semantic objects. So in this 32 by 32, which I've just shown you, we can actually do something with that layer, and we can see that the clusters do correspond to semantic objects. So how do we label the clusters? Well, we have to do this once offline, and we do this per GAN and data set. So in other words, take it again, we take the data set faces, we take the data set bedrooms, we take the data set cats, and we'll do it once. So we use a large batch of generated images, about 200, and then we qualitatively evaluate the cluster mass at different layers in ranks k. And we just choose the most semantic setting. So that you have to do, but you can do it offline and it doesn't take that much, right? Usually if you just look at a few images, you can see which cluster, which k actually corresponds the best for semantic region of interest. And so this is an example now, so we can label the clusters. Once we have the cluster, we can illustrate them, and then we can easily label them, okay, eyes, here the green, nose for the orange, and mouth for the purple. Now, we still need to do is we need to order the channels by the contribution that they have to the cluster. We can also do that once offline, and we also do this again by GAN and dataset. So at each layer, we compute the contribution MK of channel C towards each semantic cluster K according to their overlap. Oh, I'm sorry, I think there's a, no, that's correct. According to their overlap. And then we assume that each activation C, channel C, has zero mean and unit variance, which actually just means that M will be between 0 and 1. Keep in mind, sorry, C is N is the number of images, C is the number of channels, and H and W are the spatial dimension. And this clustering, you know, generates a tensor of cluster memberships U, where K is user-defined, and the K-dimensional vector is a one-hot vector which indicates to which of K clusters a certain spatial location in the activation tensor belongs. So the cluster membership encoded in U allows us to compute the contribution MKC of channel C towards each semantic cluster K. And then at the end, at each layer, we basically resize the cluster mass to the layer's resolution using bilinear up or down sampling. So let me show you now some examples. This is the best overlapping channel with eyes. This one with nose, and this one with mouth. Now, we need to have a semantic mask for localized editing. So in StyleGAN and StyleGAN 2, the global style transfer at some layer amounts to a simple interpolation between the style vector sigmas. So the S here is the target image to edit. R is the style reference, and G is the edited outcome. So basically you have S, and then you have some lambda, which basically multiplies the distance between sigma R and sigma S, depending on the strength. Now, to enable localized editing, we condition the interpolation with a positive semi-definite matrix Q. So we exchange lambda by Q. And the way we choose Q, we actually set Q to be a diagonal matrix with Q1 to QC, C again being the number of channels in the diagonal. So this Q should then favor the channels that affect the object of interest while ignoring channels that have an effect in a different kind of, for different or outside of our object of interest. Now, with respect to the object captured by cluster K, the vector MK encodes exactly this information. So that's where we're choosing it from. So we choose QC by solving the following objective. So the argument of MK minus rho 1 minus MK, such that it's basically what that does is we first set the most relevant channel to the maximum slope of 1, then the second most relevant, and then the third most relevant, etc., etc., etc. While the total non-local change is smaller than epsilon. And then we have actually an additional zero weight that assigns to channels where MKC is smaller than rho over rho plus 1. Just basically, it improves our robustness and it ignores irrelevant channels. So that's a little kind of trick we did. Now, this is the example I already showed you. So we have the reference, we have transferred the style from the reference over to the target. Again, remember, these are generated outputs, so they're not real images. And then you can see the eyes and the nose and the mouth. Now, remember, this is localized editing, and sometimes actually the differences are quite subtle. And also, not each one of these features is equally disentangled. What you can also see is, even though on this one, we're actually only changing the eyes, you might see a little bit on the nose, nothing actually here in the mouth. But on this one, you also see, for the nose, you also see that the mouth has changed a little bit. But it all looks actually quite natural. And here, when you change the mouth, even here, the nose has actually changed a bit, again, compared to the target. But that's to be expected, right? You want to have a, symmetric, if you will, face. So you don't want to just, have something locally. When you change the mouth or the form of the mouth, you actually also influence some of the other features in the face. So this is the channel C that corresponds to it. And here is a comparison again, which you've seen in the beginning in the movie with copy and paste methods. So the one on the right-hand side is a Poisson blend. As you can see, this is really not working because it just doesn't, just exchanging one part of the face does not take into account, as we said before, the overall symmetry of the face, and even the feature blend, which is basically a relatively new method, but needs some external kind of help, does not really work very well in this kind of subtle editing. Now, one of the good things is, because we actually are implying a global style editing, of course, we're having this Q matrix that actually then influences the local aspect of it, we can totally extend to unaligned references and target images. So in this case, we have the reference, we have the bedroom, the LSUN bedroom data set. So we have left a bedroom and right a bedroom, and we can change, we condition on bed. So as you can see, the bedspread changed. We condition on pillows. So the pillows changed, and we condition on window, and the window changed, even though in this one, there's not even a window. So, and these now are not even aligned. And here are the corresponding channel maps. And the same thing here also. This is now a StyleGAN 2 example. We extended to StyleGAN 2 once it became available. And you can see here the reference, and you can see the target, and you can change the eyes, you can change the snout, and you can change the body, even though they're totally unaligned. And here was the corresponding channel. So as a conclusion, we have demonstrated that StyleGAN's latent representations spatially disentangle semantic objects and objects part. And we basically leverage this finding to introduce a really simple method for local semantic part editing in StyleGAN, StyleGAN 2, that produces, we truly believe so, realistic looking output. What's important is that we actually do not retrain new GANs. We basically take in pre-trained GANs, and we only require some, we do require some human supervision, but actually only minimal and only in, we can do it offline and only in the beginning. And then again, as I mentioned just in the end, our method extends to unaligned reference and target images. Now, we could theoretically extend this work also to semantic editing of real images. There has been some work done also by the StyleGAN people of actually using these architecture, often feeding in real images and editing the images. We haven't actually pursued this yet, but this is totally possible. So thank you very much for your attention. Here is the GitHub page for if you want to know more, and you're going to get the the videos there, the papers there, and also the code there. And yeah, with that, I'm all done, and thank you for attention.
Thank you very much, Sabine. Yeah, again, please, if you have questions, please put them in the chat. Ideally, you can also put them a little bit earlier so we don't lose time. Let me start. If there's questions from the speakers, actually, so you can also just ask in a Zoom if you want. So one thing I was wondering is what magnitude of style changes can this method handle? So for instance, if you have the mouth closed and you want to open it completely so that something new, like the teeth, become apparent, start showing, which haven't been there before, or for instance, like the body of the cat, wasn't clear to me what has actually changed with the body of the cat, or if you would try to change a little bit the perspective. Did you look into these things as well? Could you potentially also change like 3D properties?
Okay, so first thing is the changes are relatively subtle. So if you look at the body of the cat, see how it's a little bit fluffier than the original one. Yeah. It just seems to be a little fluffier. That comes from the thing, but they're extremely subtle, right? Even the snout here, when you look at the original one, it just becomes a little bit more, young cat snout versus original snout. But the changes are incredibly subtle. One of the things is, can you actually change it to make a closed mouth open? Yes, you can. And even that the teeth do, but it will never quite look like the original. So if you have to think about it, in manifold, it really isn't just a cutting and pasting. It goes in the direction of. You can control this, by the way. We can also control how much you can do it by playing around with these Q factors, right? So you can actually play around how much style you're actually changing. One of the things is, it is mostly subtle changes. Now, moving, rotating people or moving into the direction, not with this method. There is a new paper I saw just on Archive, which used, for a similar idea, but a different technique. It's called GAN space. I think it was just in Archive. I saw it a couple of months ago, where they actually they did PCA. So again, some type of disentanglement, but in StyleGAN 2 on the W vector. I don't know if people are familiar enough with the StyleGAN 2 architecture, but you're basically having your latent variable Z goes through some fully connected network, so you can create a intermediate representation of W, which you then feed into each layer. By doing some PCA on that W, and depending where they're feeding it in, they actually can manage to rotate the faces and make something older. I mean, our method cannot, but theirs can. But what I found really interesting about the paper is, to a certain point, I looked at it almost as a continuation of this work, right? I mean, you start clustering, distangling different parts of a GAN to get different representations, but you know, semantically meaningful representations.
Yeah, that's interesting. Is there any question from the speaker side? There's currently no question in the chat, so then I would like to thank you again, Sabine, and we will move on. It's also time. Move on with Vito's talk. So Vito, can you please share your screen? I think Sabine has to close it first.
All right.
Thank you. Hi, Vito. Yeah.
Hi.
Briefly introduce Vito.
Can you see my screen?
Yes, you can see your screen. So Vito. Vito is a senior staff research scientist at Google, where he leads a research group on visual learning. He received his PhD